We know that 60% of cancers are not preventable. These 60% are largely driven by cell intrinsic mechanisms. They increase linear with age, and these 60% you won't get rid of because you cannot prevent your cells to age. You cannot stop time.
You started this episode saying that cancer is a genetic disease. Thomas Seyfried said that it is a mitochondrial metabolic disease. What's your take?
He's basically 30 years behind. Thousands of publications have shown that cancer is a genetic disease and that mitochondria are not the origin of them.
What is the most overhyping in the longevity and then also cancer early detection?
Doing something with your mitochondria. But if it comes to an early detection screening, I think it's...
If someone said, I want to do everything I have in my own hand to reduce my likelihood of getting cancer, what would you say to that person?
You shouldn't bother that much. 60% of cancers are not preventable. But then you have the other 40%, and these you can obviously influence. They are...
Moritz, welcome to the show. Can you explain in 60 seconds what you are doing on a daily basis so even our grandmothers gets it?
Even your grandmothers? Well, I'm a cancer geneticist. A geneticist is basically trying to understand how changes in the DNA of your cells. So every cell in your body has a set of chromosomes and DNA, which is basically the building blocks of our life. And I'm trying to read them out like you would read any book and try to find the errors and the grammar mistakes in that book to actually understand what it means for health and disease, in my context, particularly in cancer.
You not only did your cancer genomics PhD at Cambridge, you also did an MBA. Plus, you're now building your personal brand online, mostly on Instagram, also debunking a lot of stuff online, which we will definitely get to later on as well. Yeah. Most people pick one lane and kind of stay in their lane. So my question is, what made you decide to not only stay in the lab for the end of your life?
Well, first of all, I'm not technically in the lab because I'm, nowadays I'm lucky enough to have people who actually do the experiments for me, and I'm, more or less a data analyst. I do the data analysis on a day-to-day basis. I do coordinate the experiments, etc. with them, but I'm not actually the one who's in the lab and physically doing them these days. But when I started doing my PhD, I basically was very fond of bioinformatics, of the field of cancer genomics. I was very interested in healthy tissue sequencing, which is what we're doing. So, sequencing, reading out the DNA of healthy cells in any organ in our body, whether it's the liver, the lung, or anything else you might think of. Very interested in that, but at the same time, science can be very detailed, or you should be very detailed, and you should have a certain passion for it. Otherwise, you won't get very far. Although that is one aspect of your personality if you're a scientist. There, for me, was always a second aspect of it, and that's the impact on society and the broader picture of it. Essentially, since you go so deep into something, you can only get ingrained in that, and you can focus too much on what's in that specific field rather than moving outside and taking a step back and really thinking about what's the application or what's the bigger meaning of what you're doing for anything else. And I kind of needed a second thing on the side to do. So I decided halfway through my PhD to start an MBA, mainly due to that. So to have a different exposure, to learn about different things, particularly on the business side, because I was always very interested in spinning out the science. I'm currently doing, and spinning out the science I was doing back then. So for me, it was a way to combine both interests at the same time. And here we are today, and I'm still trying to pursue that dream, if you want so.
Yeah, here we are. That sounds really cool. Very interesting background. As you've risen on social media in the past couple of months, you're often focused on how more important evidence is compared to opinion. And we often see you debunking other videos that people make where they share opinions rather than evidence. What got you started doing that in the first place, and what annoyed you so much that you said, okay, enough is enough. I'm going to turn on the camera and I have to comment on this?
I have to say, nothing really annoyed me so much that I at some point thought, okay, this is the time I have to do it. This is the place and the situation where I cannot handle it anymore. At the end of the day, I think as scientists, we stay away from these kind of media putting things into a population perspective as much as we can, mainly because, this detail-oriented part I was talking about is like, if you break it down only a little bit, it's not accurate anymore. And scientists like to be accurate. But if you then go into a social media world, you're not particularly explaining every aspect of a certain thing you're really passionate about, but no one would understand it if you actually explained it in that way. So I think that is one of the reasons why scientists stay away from it, and why I generally also didn't consider it very much to share anything on social media for the broad public. But then it was mainly out of luck, not a lot of luck, but pure randomness of life. I turned 30 last year, started to post mainly different content on social media, actually heavily investing quite some time into it. And then at some point I got to the point where I met someone who had loads of expertise in this, and he was like, yeah, I saw your profile. I saw that you have cancer researcher or cancer scientist in your profile description, but you're actually not talking very much about it. And while you might be reasonably good looking, reasonably sporty, and reasonably interesting character, your main differentiator is, and the main helpfulness you can have for the broad society or broad population is, after all, sharing your knowledge. And this kind of got me into exactly doing that. Trying to help others understand cancer better is what I'm primarily interested in, and whatever ways I can do that with is fine for me. And that's essentially how I started, and why I'm still doing it. Because at the end of the day, even if it wasn't like one specific thing which got me so annoyed, there are still on a day-to-day basis things which I find absolutely horrible and absurd, and things which are discussed on social media which are broken down for the public in such a horrible way. There's no evidence behind it. There's just wishful thinking. There's, harmful information wherever you look. And even not necessarily from non-professionals, but even from healthcare professionals, there's so much. I'm not without mistake. I'm not without error, but they do present things in just a very horrible way. And I don't believe that is good for anyone. Neither for that, well, for them probably, because they make a shitload of money out of it, but for anyone who's going to them and tries to get a treatment or get, insight into their disease, it's basically wasted time and wasted health.
That makes a lot of sense, and we will most definitely talk about some of the things which are on social media nowadays, especially on big podcasts, but we'll get to that in a second. First, we need to talk about your own field, which is cancer. So, Moritz, what actually is cancer? What is somatic mutation everybody in cancer research is talking about? Especially in plain language would be great if you could explain that.
So I'm primarily interested, as I said, and now not in a language which I would tell your grandma about, but I'm a bit more specific. I'm interested in how somatic mutations, so changes in your DNA, accumulate throughout your lifetime in your DNA and across any organ in your body. So it might be, again, your lung, your liver, your esophagus, whatever you can think of. And this is basically a consequence of cancer genomics. So the field of reading out the DNA of cancer cells has been leading myself to, and many others as well. You have to imagine that about 25 years ago, we sequenced the first human genome. For those of you who are listening who don't know that, that's about 25 years ago. And then from then on, we have started to analyze, and by we, I mean, people way before me, the DNA of tumors, have started to understand how these are different. The DNA of tumors is different to DNA of normal cells, and I've seen that there are loads of alterations, somatic mutations of different scales, so single changes of individual bases in the DNA, multiple bases being changed, whole chromosome arms being altered. All of this being features of how a cancer genome looks like. And that was, probably the first human cancers were sequenced in the late 2000s, so 2006, 7, 8. And from then on, we basically rolled back and have started to understand what kind of disease cancer is. And at the end of the day, it's a genetic disease. It's driven by something you would call somatic evolution. So, evolutionary principles as Charles Darwin described them, hundreds of years ago. So you have the component of mutation and you have selection, and these are acting on every cell in our body. So your liver cells, they compete with each other and they mutate. The primary factor for that, or the primary component, is age. So with age, we accumulate somatic mutations, mostly small scale, so individual changes of our bases accumulate in this DNA. And essentially, with time and with different other mechanisms, these might give rise to something we would call a cancer cell. And this cancer cell has certain features which have been described in the past, which you would call the hallmarks of cancer, which are actually not too dissimilar from the hallmarks of aging, mainly because cancer is a disease which is driven by aging primarily, but it's essentially a genetic disease at the end of the day, which is ingrained in how we as humans are built. We are built as a multicellular organism where every cell basically doesn't care about whether our organs function properly. The cell just focuses on itself. And that's something we call, in the field of somatic evolution, probably selfish clones. So selfish populations of cells, which just live for themselves. A bit like humans, actually, in the population. We live for ourselves. We might interact with others, but at the end of the day, everything is very self-focused in our world. And the same is true for the cells in our body. They are self-focused. They do what they want. They compete with their neighbors, and they might get selected for and expand. And at some point, they might acquire additional mechanisms which allow them to proliferate even more, which proliferate uncontrollably, which allows them to escape things like the immune system at a certain point, and other things which are all have been described again in the hallmarks of cancer. But this is, in a broad picture, what we are interested in the development from, or what I'm interested in and working on in the development of cancer from the very earliest stages when you're still healthy to what happens when you're later on in life and you might be diagnosed with cancer. Can we use the information on the way throughout your life to basically predict or stratify you based on higher risks? We do that with non-invasive samples, mostly like a buccal swab or breast milk for breast cancer, urine for urothelial cancers, and other fluids which you can collect basically everywhere at home. Try to understand the damage you accumulated, and then go and see whether we can risk stratify you and provide, additional help, interventions, treatments, which can lower your risk accordingly.
That might sound, compared to what other people hear on social media, a bit discouraging that it's purely genetic and driven by age. If someone said, I want to do something, I want to do everything I have in my own hands to reduce my likelihood of getting cancer by as much as possible, and I'm willing to go any extra mile required, what would you say to that person?
I would say what I live my life according to. You shouldn't bother that much. At the end of the day, we know that 60% of cancers are not preventable. And that's a reality social media or anything in society often ignores. Mainly because these 60% are largely driven by cell intrinsic mechanisms, which we can basically not explain. They increase linear with age. And there's no way we currently know, there might be some in the future, but no way we currently know how to circumvent that. And the 60% you won't get rid of, regardless of what you do, because you cannot prevent yourselves to age. You cannot stop time. Regardless if some people would love that, you cannot do it. But then you have the other 40%, and these you can obviously, influence. But they are really easy to influence. And honestly, they are probably pretty boring for the majority of people, because you shouldn't smoke. You should avoid chronic infections if you can. You shouldn't drink. you should be in a shape which is pretty much an average BMI between 20 and 25. You should use your sunscreen, and you should use all the methodologies for screening which there are available. If you do that and eat a healthy diet, again, which is very closely linked to obesity, basically, which I was pointing at, then you do everything for you can do effectively. And, even if you have an exposure here once in a while, it won't change a lot of things. It's the chronic things throughout life which increase your risk, not like individual days. It's a compound system, a compounding over time. And I always like to explain it in the way that there is a baseline rate, if you have an x-axis with age and a y-axis with damage, basically with somatic mutations, then age itself is a linear increase. Has a baseline rate. But then if you add on like different other things, like, smoking, you increase that rate by X%. And this increase is compounding over time and increasing your risk the longer it goes. So the same is true, although not always through the means of mutations. There are also other ways a carcinogen can act on cancer, but you basically have these few risk factors which are already good enough to avoid. And if you do that, you avoid 95% of it. The other 5%, honestly, your risk is already so small, then the risk you can influence in comparison to the 60% others, probably not worth it worrying about it too much. If you want to, you can. That's everyone else's choice. But I wouldn't do it because the odds are not in your favor.
You've mentioned chronic infections. What exactly are you referring to?
Like human papillomavirus, other viral infections like hepatitis B, hepatitis C for the liver. You have EBV, Epstein-Barr virus. Then you have
most have at some point, right?
Yeah, although it's associated with some. Well, it's definitely an exposure which many people have. Yes, as is HPV. So that's also an exposure most people get exposed to throughout their life. To a certain degree, the chronicness is different, obviously, and I think the amount of reinfections you have can be different again. But it's the chronicness which makes the difference, and obviously a bit of luck if you get there are HPV strains which, for instance, are not carcinogenic, whereas there are a few which are extremely carcinogenic and make up to 70% of all. I always mix up endometrium and ovarian in that context, in the English word always I don't know, it's one or the other, or cervical. Which one is Gebärmutter? I don't know.
Ovarian, right? Is it?
I think
so. I think it's ovarian. Yeah. No, cervical. Sorry. It's always something different. Cervical cancer.
Makes a lot of sense. So people should try to avoid this as best as possible. Get your vaccines as well for HPV virus.
Very effective.
Very effective. When people talk about cancer, two concepts often come up as well, which is the words of driver mutation and then passenger mutation. Before we get into the social media claims, which we will dive into right after this, first want to make sure that everybody understands those two concepts. Could you explain that as well?
You have to imagine that 99% of your DNA are basically, some would say, random shit. They don't have any functional meaning as far as we know. There might be some sequences anywhere in the genome which have, but so far they play, at least in cancer as we understand it today, a very minor role. These mutations I alluded to beforehand, which accumulate throughout life, in 99.9% of the cases they hit a sequence or a base pair in the DNA which don't have a functional consequence. They basically, they just change a base, nothing happens, your cell functions in the exact same way. But then there are obviously some regions which are very important, which are referred to as genes, and these genes have functionality because they are the ones which are actually translated into proteins. Depending on base pair changes in the gene, you might have a slightly different protein, or even a misfolded protein which doesn't function in the same way as it used to before. So through cancer genome sequencing, we basically started to understand that there are loads of mutations which affect specific genes in the about that of 20,000 genes which are in the human genome. Amongst those, there's a number of genes which we refer to as drivers, so driver genes. These driver genes are called in the way because they sit in the driver's seat of cancer developing. So they are essentially the ones which are under something, and again, that refers to the evolutionary theory of selected for. So the selection aspect. So cells mutate, and depending on whether they have a functional consequence and can actually do something better, have a better feature in the local environment they are sitting in, they might get selected for, just as any animal in the wild gets selected for if they develop a better trait. And so some of these genes which we described are basically the driver genes of cancer, and you can define this set of driver genes for almost every cancer type, which is what we here at the Sanger Institute, where I'm currently working at, have extensively done in the last 10, 15, 20 years or so. And essentially, all the other mutations affecting other genes are referred to as passengers because they just randomly accumulate. They don't have a selective advantage. They're basically neutral, and they still accumulate over time, but in the background of a driver, which actually gives the selected advantage. That's the major difference. So you can see it as a running car. You have a driver in the driver's seat and the passenger sitting next by and just letting you get carried to wherever you want.
I really like the analogy. And that might also be something that might be useful for the next section, which we want to discuss, which is wanting to bring kind of some of the statements that are all over social media at the moment. We would love for you to comment on that. So a few days ago, Thomas Seyfried, which I'm sure you've heard of, went on the Diary of a CEO podcast with Stephen Bartlett, and he talked a lot about the metabolic theory of cancer. So you started this episode with saying that cancer is a genetic disease, and Thomas Seyfried proposed a different view. I'm going to read out a few of his claims, and without any other comment, I would just love for you to share your view on this. So Seyfried said that cancer is not a genetic disease. It is a mitochondrial metabolic disease. The origin sits in damage to the mitochondria. The mutations everyone chases are downstream effects of that damage, not the cause. He frames this as reviving Otto Warburg's 1920s work, which he says the field wrongly buried when it adopted the somatic mutation theory. What's your take?
It's the second time Thomas Seyfried is on the Diary of a CEO. It's not the first time. And the first time was a disgrace, and the second time is a disgrace. Basically, I don't know why Stephen Bartlett is doing it. I don't know what's the rationale behind it, but he's giving someone who has no stand in cancer genomics and cancer research at all, who has been a professor, who hasn't published any meaningful paper in the last 15 years on the actual subject, who's giving him a broad audience, a million audience, and letting him tell them essentially what is factually not claimable anymore. When his first interview or podcast with him came out, I already watched that, and I was basically shocked about what he's essentially claiming, because he's basically 30 years behind. I think his theories were valid when he learned and when he published, but in the meantime, he has essentially neglected anything which comes from the human genome, which we have, which hundreds of publications, thousands of publications have shown that cancer is a genetic disease and that mitochondria are not the origin of them. Because we can sequence mitochondria, we can see whether they are functional, we can check that, and all of this in most cancers is still intact. What he basically proclaims is the Warburg effect is something which is very, very present on social media, because there's obviously a very easy thing to see, which is like sugar is metabolized through the Warburg effect, and you can see it in PET scans, and that's the rationale, while most people always say, okay, cancer is a metabolic disease, or the Warburg effect is true. And obviously the Warburg effect is a real effect of glycolysis happening in tumor cells, but it also happens in other cells. Funnily enough, in that context, if you look at the whole story, it's basically always the case that Otto Warburg got a Nobel Prize, but he didn't get it for the Warburg effect. He got it for his research on electron transport in the mitochondrial OX-FOS pathway. And essentially from that, people always claim that, first of all, it gives it credibility. Second of all, it's this effect, which we've seen. And now, in the 2000s, we have seen that PET scans can essentially visualize tumors with radioactively labeled glucose, and that's clear as day. So they must metabolize glucose in a way, and they do, but they actively decide to do it, not because back in the day, Otto Warburg stated it to be a problem of dysfunctional mitochondria. But what we know, actually, he himself, 30 years later, disproved that kind of by showing that normal tissues actually can do the same thing. They can also do glycolysis in some circumstances. And actually, your brain, for instance, does it quite often. But nowadays, we know very well that it's an active process. It's an active decision in favor of glycolysis, which is not due to dysfunctional mitochondria, but because the tumor prefers the fast energy availability. Glycolysis is extremely inefficient. It produces like 2 ATP in comparison to the entire OX4 pathway producing about 30, right? That's a 15-fold difference. The only difference is really that it's much faster to do that via glycolysis and a few other minor points. So dysfunctional mitochondria, and I've done quite a bit of research on mitochondria. I've published in that field, and I know, quite a bit of things about this. They are not the origin of cancer because they are not dysfunctional in cancer cells. There are thousands of mitochondria in your cell, and not all of them behave wrongly. Obviously, they misbehave based on the alterations which you have in a normal cell over time, but we can be pretty confident these days that the first alterations happen in the nuclear genome, in the normal DNA, not in the mitochondrial DNA. And that's where he gets, there are lots of other things he gets wrong in that assessment, but I think it's mainly, and I don't want to say, everyone who studied or who learned like 30 years ago is wrong, but he clearly has dismissed the idea that it doesn't have to be that way, and it doesn't have to be a metabolic disease, as so many others have. Many others change their mind. That's how science works. You see something, you try to prove it. It might be proven for a while, but then there's some other evidence coming up and it disproves it again. And it shows maybe something slightly different, maybe something completely different. And that is how science evolves over time. The difference between a good scientist and a bad scientist is just whether you are able to adjust or whether you're stuck in your own head.
I think this is the most important sentence everybody should put in their heads. When Seyfried is asked about evidence, what he's often bringing up is an experiment where he's saying that one should take the nucleus out of a tumor cell and put it into a healthy cell body, so cytoplasm with good, quote unquote, good mitochondria, and then you don't get cancer. Do the opposite or the reverse, so put a normal nucleus into tumorous cytoplasm and you get dysregulated growth. He then argues this proves the control sits in the cytoplasm or the mitochondria and not in the DNA. How is this wrong? Because it sounds so convincing to the layman.
I mean, there's a lot. The problem with these statements is that you can almost impossibly fact check them while they are spoken. So I don't even blame Stephen Bartlett for not fact checking it, because it's deep science. Even now, I can tell you that yes, these experiments have been done, and they, to a certain degree, show what he's claiming they show. But then at the same time, there are problems about reproducibility. There are problems about, what kind of conditions these cells are cultured in. There are, the problems about it being a cell culture and not necessarily proving in vivo conditions which are happening in the human body. In the first example, what happens quite often is that the malignancy happens after some time in culture. It's not a constant state. If you look at the literature in that regard, there will be situations where, in 3 out of 4 conditions, it might go this way. In 1 out of 4, it might go the other way, and the malignancy potential goes back. I think what you can take away from it is it's basically, no one says it's a single mutation which is causing cancer, and it's not, necessarily just genomic rearrangements. It's an interaction in a constant cell environment where, the interaction between the cytosol and the nucleus is constantly happening, and abrogating it or making it dysfunctional, like an insult like this is to take the entire nucleus and put it into another cell, generally will give you both scenarios more often than not. And that's what the literature in that regard has shown in the past. So I don't think it proves anything. It's not an experiment that shows, okay, mitochondria are basically regulating anything in cancer development per se. There's no question that they have an influence. That's, without ask, but they are not the driver. To come back to the initial analogy.
Maybe also, especially on social media, there's like people going for extreme takes, right? It's either all or nothing. It's either 100 or 0. But maybe it's also that there could be some things that can be used from both sides, right? And I thought that Seyfried made some interesting claims around what he said, that cancer runs on different fuels, it can be glucose, can be glutamine, and that in adjunction to standard cancer treatments, you could use strategic tools from a certain diet, in that case a ketogenic one, to like not ingest any glucose further, and then also in a pulsed way use repurposed drugs that block the glutamine to maybe increase likelihood of treatment success from conventional treatments, or even reducing the dose required. So I thought that was interesting. Do you think that these things are sufficiently explored in cancer patient populations? Because they would be cheap to implement, they wouldn't cost too much, and likely the results wouldn't be, or they would not involve too much risk compared to super novel therapies where we have never used anything similar before, right?
Well, to answer your first question, they are explored in specific contexts. I think, a broad statement or a general statement about, you should use a ketogenic diet or press polls, whatever he calls his approach to treat cancers generally is, I think, not adequate, mainly because cancers are metabolically flexible. They are not the same disease. There are some who are more likely to respond to such a treatment. There are others which are not necessarily very likely to respond. Well, I know that in brain tumors, ketogenic diets, basically in mice, have shown some really good effects, which has subsequently been trialed in small clinical trials. I think it's called the ERGO2 trial, which uses a very similar idea, again, for brain tumors, for glioblastoma. But this trial was negative. It didn't reach the endpoints which should have been reached, or which should have been reached in order to show that it has a particular benefit. Having said that, maybe it was just unlucky. The patient selection criteria weren't perfect for the kind of intervention. Maybe there were other factors which are playing a role. It might be that that's just not ideal. At the same time, it might also just mean that, this intervention is not necessarily good enough to provide a better outcome. So I think it gets explored, but obviously it has also gotten a big hit from this metabolism mainstream, which has been existing around the 2000s, but, primarily driven by this PET scan investigation. There has been active research into compounds which are actually triggering, medication or drugs which are triggering metabolic related pathways, but they haven't really shown anything in the clinic. So they died out. It has still been very enriching. People have learned a whole lot about other factors, but it just hasn't shown the effect people would have wished for. So at the end of the day, I think it's a claim. I think it has its place in specific scenarios, but not in all. And whether it's really reliable or anecdotal is, still out there. And I think the evidence is probably rather in disfavor than in favor of using it. And there are obviously, if we talk about providing certain diets to a cancer, a ketogenic diet to a cancer treatment, there are obviously other risks associated with it, which are much more severe, like cachexia, which probably make it not applicable to a lot of cancers, and probably a net disadvantage rather than a net advantage.
It's always interesting to discuss quote unquote novel things if there's actually evidence, maybe even debunking them. I'm a big proponent of that. If there's a topic which may be interesting but hasn't yet produced any evidence, that it's still interesting to discuss and still interesting to propose any hypothesis. I mean, this is also how science works, right? So I was just thinking about, in the beginning, you said 60% of cancer is unpreventable. You can't do anything. Do we have 100% proof? Do we have 100% evidence on that fact that we know that 60% is unpreventable and the case closed? Or are we not sure yet what we should do with the 60% where we can't explain it yet, maybe?
Well, I think you have to differentiate between what not preventable means and what that means for a population at the end of the day, right? These 60%, it's also, it's an estimate. That doesn't mean that it's not 55, that it's not 50, that it might be 65 or 70. There is some uncertainty around that estimate, obviously. But then at the same time, yes, the majority of cases happening through age. And again, we've seen that even the early models from the 1950s, where you have just been explaining cancer incidence with age, they really nicely explain age incidence curves or cancer incidence curves, probably even today, with a few numbers of genetic alterations happening in specific cells, in specific genes. That's still true today. We see it in our research these days, and that hasn't changed. So as long as we don't find a way to avoid those genetic changes, which we cannot because we don't know where, for us, they are cell intrinsic. We don't know the mechanism they are existing by or why they exist. We know at which positions they occur, but we cannot specifically say, okay, this is how we can avoid this damage to happen by improving X, Y, that. As long as that doesn't happen, I think there won't be a change, and this fraction will stay the same, and that is pretty much for certain. But what I essentially wanted to allude to or wanted to go at is there's still a difference between 60% non-preventable cancers and what we do with those cancers and at which stage they occur, which is what I primarily advocate for, because there is a huge difference between early stage cancers and late stage cancers. Late stage cancers have almost ubiquitously 10% survival after 5 years. Most people unfortunately die from it, whereas early stage diagnoses have a significantly better prognosis, and people survive a lot longer. There's 90% 5-year survival for most cancer types. And so this is basically my way of saying, these diagnoses might stay the same and they might occur and they will happen. But if we can make a huge difference in what kind of diagnoses are happening in someone's life, then it suddenly doesn't become an event which you have to be fearful of, an event which has to accumulate loads of treatments, which has to where someone has to undergo a whole lot of, to be honest, miserable things in order to be cured from their cancer. And so at the end of the day, I would say, these 60% are pretty much up for grabs. They will be there. There are some, if I would dream, there are some theories how to prevent it. And I can name you a few, but
please do so.
Well, at the end of the day, I don't know if I want to put that out there, but obviously we are thinking about it constantly, how we can essentially justify or establish something you would call chemo prevention. So the preventive medication to lower your cancer risk, which is the second the other side of the coin in comparison to risk prediction. You have risk prediction, but if you know what risk is actually mirrored by, can you modulate that risk through something else? And this is actually something we are actively trying to understand, how something we call clonal landscapes in normal tissues, so the abundance of different cellular populations with driver mutations, which are there in every one of us, and they increase with age. We see them, we can definitely define them. How after this definition, we can then start to develop preventive medication to essentially say, okay, these are the cellular populations which cause cancer. We know that they occur in the tumor of that tissue. They have these and these driver alterations, and we see some of them, not all, and also not to the same proportion in normal tissues then? What is the link between them, and can we just reduce the abundance of these normal cellular populations with driver mutations to essentially lower your risk and lower the risk of cellular dysfunctionality or organ dysfunctionality? And I don't think we are pretty far away from having preventive drugs, but I think we are getting closer to understanding how we need to modify, or what kind of aspects we would need to modify in order to get to the point of reducing risk at some point in the future. And I can name you a few. You can think about a few examples in day-to-day life how medications are actually probably already doing that. And there are also FDA-approved chemoprevention agents. There are just very, very few.
Such as?
Anastrozole for breast cancer, for instance, or tamoxifen, which is a chemotherapy, but is used as a FDA-approved as a chemoprevention agent for estrogen receptor positive breast cancer. So, mechanistically, it makes a lot of sense. They are essentially endocrine therapies which avoid, hormone receptor positive cells in your normal tissue to proliferate more than the rest. So they level basically the competitive field. And that's essentially what we would consider the ideal scenario. You don't need to kill anything. You just need to, if there are cellular populations which have an advantage over the rest, the wild type, then you need to reduce that selective advantage to the same level. And then it's plain level field. It's a balance. It's what we call homeostasis, which is the constant state in any healthy normal tissue. This is probably how tamoxifen works. This is, how a few other drugs like metformin for head and neck cancers likely work. There are, I can't think of many other examples off the top of my head. Aspirin for colorectal cancer is very, very similar, has been shown to be a chemoprevention preventative. So there are these examples, but most of the, you have to think about how we got them, how we got to these examples. And the answer to that is through years of waiting. So you apply these drugs to people, obviously on a very low dose. No one is getting a chemotherapy fully blown like tamoxifen for years, but a very low dose of these drugs. And they take them for many, many years, and we follow them. They were followed up for 15, 20 years, which is the time scale on which cancer develops. And then you see whether the placebo versus the actual drug had lowered the cancer incidence of the cancer you were targeting. And for these cancers, they did. For aspirin, it did, although that was more of an accidental finding.
It's interesting also that these were, you've mentioned metformin, you've mentioned aspirin, which have been discussed as potential future off-label medications for aging or healthy longevity, so in the health span context, because they have looked at, patient population data, and they have seen that people who have taken metformin have lived longer than some who didn't, even though they took it for that to control their type 2 diabetes. And it's interesting that, again, we briefly touched upon this in the beginning, that there seems to be, with regards to some of the mechanisms, there seems to be this overlap between kind of cancer research and aging research. And you've mentioned, you've beautifully illustrated this X and Y axis with time and the cancer risk, and that kind of with age, you have kind of a constant increase in cancer risk over time. Then obviously, depending if you add a few risk factors, that line gets steeper and steeper. But it's very interesting to me that if one had just heard that statement and is already deep into the longevity game and wants to optimize everything, wouldn't that person conclude, hey, the one thing I should do as aggressively as possible is to lower my, call it rate of aging, biological age, however you want to call it. Obviously, the question is, how do you measure this? How can you prove it? Where's the evidence? But wouldn't that be a reasonable takeaway based on what you have described?
So you mean just taking metformin and aspirin for the rest of your life?
Not saying that. I'm saying that if I wanted to reduce my cancer risk by as much as possible, I would need to, in a theoretical world, treat aging by as much as possible.
I would say Yeah, probably. You would, at the end of the day, the biggest risk factor is aging. If you can slow it down or, remove the risk from aging, which aging poses on many, many different levels on the cell, not only through what pathways metformin or aspirin are tackling, you could certainly be able to avoid your cancer risk. Having said that, there are always two sides of a coin. And only because you avoid cancer risk, it doesn't mean that you're still going to be healthy. Because there's something you call neurodegenerative diseases, for instance, which have a very interesting paradox. The fact that in epidemiological associations, and there are some confounding factors, but even the confounding factors are not when you can account for most of them relatively reliably. And there's the cancer Alzheimer paradox, where cancer patients develop less Alzheimer and vice versa. And I think, you avoid one of the risks and run into another. So I don't think it's that easy. I personally don't think aging is reversible, or any, again, it goes back to the start of our conversation about trying to optimize things which you don't really have under control and which are outside, we as humans, and I know it's a bit philosophical, but I have to advocate that you just need to understand that we all have to leave this earth at some point, some earlier than others, and that's very unfortunate, but there's no way around it at the moment. And there will probably also, it won't change tremendously through medicating yourself, through hacking, through whatever. You will still go, and there's no, you have to make peace with that thought at some point in your life. And better make it earlier than very late, because I think it will give you a lot of fear otherwise throughout your life.
Yeah, I think that's a great take. I'm sure some scientists like Obi the Gray or David Sinclair would disagree with you, but that's part of another discussion. And I think aging itself is also a beautiful concept as a whole. I think just aging makes life beautiful. Without aging, we wouldn't have like any time constraint. We wouldn't have any motivation to really change stuff. So for me personally, I think aging is beautiful. We just want to make sure that we are aging healthy. So I think this is the most important point. As time is running out and we are coming to the last section, which is our rapid fire section, which means you only have around 30 seconds for the questions we will answer to you. So let me just get started with the first one. What is the most overhyped thing in the longevity and then also cancer early detection market right now? Because as we know, they overlap now. Taking things like full body MRI, multi-cancer screening, Gallery, TrueCheck, whatever you name it. There are few things out there.
Doing something with your mitochondria, most overhyped. But if it comes to an early, to early detection screening, I think it's probably whole body MRI. So mitochondria, I think we alluded to before. There's not really anything you can boost there. There are thousands of them, and there's not really a reason why anything which is out there on social media should specifically target your mitochondria and not anything else. If it comes to whole body MRI, I'm not opposed to it. I just think it's basically overused, and people consider it like this. To a certain degree, I go in there and forget that there are limits of specificity and sensitivity, and only because you do a test, it doesn't necessarily mean that there's something under the limit of detection which you cannot see. I think it's a great addition to cancers where you cannot screen for, but then it probably is a bit too overhyped these days.
Logical follow-up question: what's the one test every adult should get then?
I don't have one. I would say low-dose CT scan for smokers. That doesn't account for all individuals, I know, but low-dose CT scans as an initial screening, I think, is a great development, especially in smokers. Also advocate for anyone of a high-risk group who is a non-smoker, because we see never smoker cancers rising in the population, to actually also get low-dose CTs on a regular basis to avoid or to try to limit the health consequences of lung cancer, because it's so deadly and it's a horrible disease.
What would be risk group if a person's not smoking?
Well, either passive smoking or risk of even very air polluted surroundings could be a risk. could be, heavy asthma as a child or things like that. All of those could be potential high risk groups, but there would be more factors to take into account.
If I would give you unlimited budget and we would ignore initial feasibility, you would have all of the persons in your study group, whichever you want. What would your lab actually work on next?
Is it also that the population exists?
Yes.
Then I would certainly do a clinical trial on using breast milk as a risk prediction for breast cancer in a clinical trial setting where women take chemoprevention agents pre-post treatment over time, and we follow them up, or we actually have followed them up 20 years ago to now analyze their data pre and post and know whether they develop breast cancer or not. So you basically have two arms, one placebo arm, one chemoprevention arm. The breast milk has been collected pre and post therapy 20 years ago. Nowadays, we have the outcome, and we could see, first of all, whether we can detect the biomarkers of response in their breast milk a lot earlier than what the cancer outcome would be, because it would be a perfect proof of concept for the principle of somatic evolution being, first of all, predictable, and second of all, intervenable.
Interesting. Now, the last question, which is the return on health question that every of our guests needs to answer. And you're not a physician, but you looking at all of these numbers and analyzing the data of so many cohorts is potentially even more interesting. And that is, if there's one thing in the current healthcare system you could change, what would it be?
I would start sequencing everyone in the population at birth, because you can rule out so many, inherited diseases. You can risk stratify quite a lot of people, but you can also give information. You can just democratize risk to a degree. The second step would then obviously be later on, sequencing any individual organ, because I think it has merit to know about it, but probably at birth would be the start, and implementing that in order to, the German healthcare system is, we act once symptoms occur. We don't prevent, and we don't preemptively get active. And that is a huge issue, I think, from my perspective.
And I'm pretty sure we would agree on that take. So, Moritz, thank you so much for coming on the show. We will link all of your socials, your Instagram, whatever other socials you have in our show notes. And also we'll link your lab work in the show notes as well. So again, thank you so much for coming on. It was really, really interesting. And to the viewers, don't believe everything you see on social media.
Thank you so much for having me. It was a pleasure.